All right, welcome. This video, I want to slow down a bit. The entry video for the Hackaday Prize 2014 had to be under 2 minutes, so we had to move pretty quick to go over it. But I wanted to use this video to kind of have a discussion about the algorithms in the human connection first impression project, because I think it's very important that one has to understand this, because anyone can throw together hardware. That's pretty easy to do. But to combine your algorithm in the hardware, that's where magic is, because software is often a big black hole. So before you get started on a big project, you should really understand the algorithms and do an order of magnitude analysis on the complexity of your algorithms, so you know what you're experimenting with. So I wanted to take a few minutes to further explain the algorithms in the Human Connection project. First impression. We had about 13 seconds to go through in the entry video, so this is will be the next level. So I'm going to slowly go through this with my doodle pad and let's try to make a little bit of sense of it. So in the introductory video and in the notes that I kind of went through, or posted to the site, we start with some sensors, and for the contest here, we're going to consider a very high bandwidth sensor, such as an ultrasonic microphone, because we're interested about extending humans. Now, the ultimate vision here is a mission to Europa, and I really think if we can, put some hydrophones down in there, there might be some weird stuff going on down in Europa, or elsewhere, even our own oceans, but we're just not listening for it. So this is our first attempt at trying to understand the algorithm. So I have two symbols of some microphones kind of doodled out right here. And the first concept is that these don't have to be microphones. These are any kind of sensor into this fluidic domain. So these could be microphones, hydrophones, implemented with MEMS, electret, some sort of piezoelectric ceramic. But we have two signals. So, and I'm going to draw, just kind of like a little wave here. And I'll get a different color here, and I'll draw this wave here. And I'll call this signal beta and this signal alpha. So we have these signals alpha and beta coming from the microphones. Now, these microphones can be placed nominally where the ears are at, or not. Maybe they can be placed in some other orientation. Maybe they can be placed orthogonally at 90-degree angles. So, but we're just going to assume we have two signals. So let's start there. The first thing I want to do and consider about these signals is that they're not two signals. They are the same signal, just separated orthogonally. With J. So let's just say we can represent them on the complex plane as a complex signal. Now, what would be interesting is that also if we had a lot more sensors, that maybe we could put them, in a big tensor of some sort, and maybe do some sort of tensor calculus on them. But for now, we're just going to consider them complex valued. Now, in reality, the signals may not be orthogonal, and they may not even be linearly independent, but we're going to treat them as that just for now, because I think there might be something interesting from the perspective of the human ear if we process it as a complex number. So one way to imagine this kind of theoretical signal is I have it kind of drawn alpha plus j beta as this complex number. We're going to write, make like a little complex axis here, and please forgive me for my poor artistic abilities. But we have kind of like the real axis over here, and then the j-axis or the imaginary axis here. Now what I'm going to try to do is draw out in this direction time. And so what we're going to have here is some signals, and I'm going to draw them in blue. Because we're in kind of real and imaginary land, this signal kind of moves around the plane in time. And so you can have this rotating kind of signal, in the real and imaginary axis. So I'm going to try to draw this. And that's the perspective we have, is that we have this new kind of signal with this complex number. Now, like I said, I'm not making any assumptions right now that the alpha and beta are truly orthogonal physically, but we're going to treat them as that numerically, because there's some interesting things I think we can do. And I think the thing to keep in mind here is that we're not trying to do signal analysis to to extract some sort of metric from the signal. What we're trying to do is to re-encode out-of-band signals in band in new ways that the brain can then use. So even though we might not have a good understanding now of what that is, what we're trying to do is kind of come up with new ways to present it to the brain, so maybe we can understand the world in a completely different way. Because right now we're used to kind of decomposing, signals in our brain just kind of with like a time frequency kind of interpretation where we can hear tones over time. But we want to do a little more than that. I think we have a nice little sandbox. The idea is this hardware to have a nice sandbox to do that. And then maybe we can re-encode these out-of-band signals in band in a new way to really understand how... or to really get a new perspective on how we connect with the world. So what we're going to look at is this kind of concept. We have this complex signal, and I call it alpha, and I put a superscript n plus jbn, meaning it's a sampled signal. We're going to sample to some rate, and I'm just going to kind of call that I of n. I draw a little arrow. I consider if it's in the complex plane, it's kind of like a vector because it has magnitude and direction. So the idea with the signal processing flow is we're going to sample that at some rate, and we've got this complex signal. So the first thing we're going to go into, let me draw a box here, is a complex FFT. Now, most applications use a real FFT where they consider the input real valued, and because of that, there's some symmetry you can exploit there to enhance speed. But we're not. We're going to take a complex valued transform over a complex signal, and so we get a complex response. So the kind of next thing in the signal flow. Let me redo that one there. After the complex FFT is the remap. Now, there are lots of ways to do this, and this is the core part. I think that people often trivialize that this is actually a really hard problem. It may be easy. It may be an easy problem to do computationally, but it's a non-trivial problem to do it in a way that yields a result that's useful. So, and here's the underlying problem. So let me draw. And I'm going to draw an axis. We got like frequency, and I'm just going to draw amplitude. Phase is involved, but I'm going to skip the phase part just for now because we're going to do the identical operation of the phase. So let's draw just like this. Here is 20 to 20 kilohertz. All right. And let's take another band here that's way above. All right. And we want to pick a slice. Just like this. All right. and we want to remap this in this area. So we got to take this width here and remap it into this width. Now that is simple enough in principle to understand how that works. So what you could do is you scan through this array and you kind of like squish it down into this array. But we're dealing with discrete time signals here. So, and I just for discussion's sake, let's say this spans 100 bins and this spans 20 bins. What do you do with that data? You have 100 bins worth of data that have to go into 20. So every 5 bins, you could sample it every 5 and dump it in, or you could take a frequency average of 5, or do you do something else? And this is the key part: is what do you do? When you do this remapping. And it's really a challenge when you're going from many bins into fewer bins, because you don't want to lose anything. So there's a couple concepts I think we want to try to explore here is what do you do with that? And I think the key difference between this project and other projects is we want to really look at these algorithms and get an understanding of what works and what doesn't. Because things like bat detectors, which do like a super heterodyne, those are very simple. They're very narrow band and they move very narrow bands down into a spectrum, but it's not necessarily even a linear map. You get other weird stuff because of the heterodyne. I've seen ones that will take a signal, square it up in the high frequency domain, run it through a couple flip-flops to get in the low frequency, and that's extremely crude, and I'm not even considering that here. So, but we're really concerned about this remapping phase, and maybe do we want to do something goofy like this? And let me draw the red point here, and let me grab another point here. Let's grab a different color. Let's grab like green. And maybe we want to do a complete inversion. Maybe we want to do this and put the green here. So the end goes to the start and this start goes to the end, and do a remapping like that. Now there's a bunch of different ways. Now the other thing I was thinking, maybe in this case of where you have these 5 bins mapped to 1, maybe you encode that in some sort of amplitude or phase modulation. And now that's interesting because that's a sound that wouldn't naturally be in the upper spectrum, but we're trying to re-encode it. What would the brain do with that? And that's really the key connection we're trying to make here, is that it doesn't necessarily have to make sense from a numerical process of, we're not trying to just move the sounds down. We're trying to move them down and possibly re-encode them so the brain has an easier time dealing with these signals. Now, we can remap, once we have the infrastructure to do this, we can take many bands into here, and if we have the proper sensors, move very low into the higher band. So, but once we do that, we essentially have a complex spectrum. And I'm going to say I for inverse, CFFT. When we're all done. And then coming out of this, we have kind of some new signals. We have, I'll just call it like alpha prime plus beta prime. Let me do this. Let me go stop. Let me redraw that. That's the CFFT. And we have some new signals, alpha prime plus J beta prime. Maybe I want to put the N down here. I don't know. It doesn't really matter. We have a new set of signals that is what we feed into our ear. And here's another key distinction, is that in the iteration that we want to do for the prize, is that imagine the user wearing some sort of headphones where they might not normally even get the normal bands into their ears. Let's assume we have complete control over that. So to avoid information overload, maybe we want to eliminate, say, the 1 to 5 kilohertz band that would normally exist, and the only thing that's in there is stuff that we have remapped. Now that's a new concept, and maybe we want to filter out all that other stuff. Maybe we don't, but I think we want to investigate that because that's key. Now, the other side of the Human Connection Project, which I think sets this apart from the other ones, is that once we have this process, can we do essentially the inverse of this process? Here's what I mean by the inverse. Let me grab a new slide here. And let's say we could take a microphone in. And this could be 2. If we had a complex signal, we do our CFFT, and we do this remap, and let me draw this around here because I'm using a thicker line. All right. Let's say we have this, the exact process, but instead of replaying it into the ear, we want to replay this, through an ultrasonic transducer. Xducer. Now, why would we want to do that? So here's the next big idea. And so let's say we could put this system under the ice of Europa. And let's say we're measuring things down there. And let's say it's just above human hearing or not. What if we want to go the other way? What if we want to speak and have our speech remapped into those new bands? Now, this sounds like an absolute crazy idea, but I'm asking a big what-if question. What if we could invent some new way of communicating with things that aren't used to our normal speech bands, which are lower? What if we can take our speech and remap it up? What kind of new things could we open up? And that's something that I find absolutely fascinating. The even thought that we can do that. And here's the crazy idea, is that we already know, and this is known science, that, for example, a dolphin can use sonar, and not only sonar in the audible band, but up above human hearing to do location. And let's think about this. Maybe they do use it for communication. What if we had a tool set to be able to talk to the dolphins? And I know this sounds absolutely nuts, but I think this is an idea that we really need to explore, because what if we had a remote mission to some new body of water where we could listen and interact? I think this is 100% within the realm of possibilities. Now, it's going to take a big tool set to do this. And it's going to involve exploring some new ideas. But we have the embedded systems, I believe, to do this in real time. And so that's kind of the magic of the algorithms we're going after. And that's what I think really sets this project apart. Now, there's one other algorithm that I wanted to explore. And this could take a long time. We could spend a long time on new algorithms, but once we have the hardware and the hardware platform, we can do it. So let's think about this. We can go back to our kind of original plan here, and we go through this process of remapping the signals, and we end up with a complex set. Now, a complex signal. Now, let's pretend whether this is a signal that is remapped or not. I don't even care. We have a complex signal. And I kind of drew this picture, earlier on. Let me draw. I'll draw it again here. Let's say we have an axis, and we have the real and then we have the imaginary axis. And we're going to like stretch it out in time here. And I apologize once again, my 3D drawing abilities are not that good. Let me draw some dots. So, put T for time. So, at time T, maybe we have a signal here. I'll do it in gray, actually. And then another time down the low, we have a signal here, and then it comes up here. But it's on this complex plane. And let me connect them. Consider this. Instead of taking the signal and playing the real and imaginary parts through other transducers, let's take it a step further. And this is starting to get into another realm of, instead of just trying to remap what's there, can we create a new type of signal that through a nonlinear transform, just to see what we'd get and to see what the brain would do. And I want to say that one more time, is I think what we're after here is to see what the brain would do with new stimulus, because we may be able to make some new kind of connection here. So here is the concept. Now, we have these signals as kind of time marches on. So, all right, let me grab a different color here. Now, consider this signal as it kind of rotates down in time here. Well, since we have a real and imaginary part, kind of draw, if we have an origin here, and let's say the signal's here. All right, so let me draw this out. And we kind of have beta in this direction, and alpha. And I'm going to draw, maybe that's like a vector. Well, we have some angle here. And we can get the angle with arctangent, right? Arctan. What if we synthesize a new signal that is just this phase angle? And this is a little bit, I should be careful to even call it a phase angle, because that's not exactly what it is. But this angle in the complex in this signal plane, what is that? And what would the brain do with that? And can we come up with a set of two new signals that are trigonometric, that the brain would do with this complex input? This is a purely time domain kind of computation. So, this could be applied before or after the remapping. So there's a start. So that's the algorithm discussion 1. This is kind of a high-level overview. I've already done some experiments with the 4370 to kind of demonstrate that at the sample rates I want to operate at, it can definitely do the real-time FFTs. I may do it on a different platform as well, just for another reference. But so there you go. This is kind of the start, and I think this is what you got to do before you go too much into any project, is really understand what you want to do. But I hope this gives you a better idea of where we're going to go with the algorithms for the human connection. So Europa is waiting.